Okay. Tim is a PhD candidate at Brown University. He also comes with his own set of groupies, as you heard earlier, with the people that introduce themselves because he's speaking. Tim received his bachelor's in physics from Cornell University, and he's currently working on examining exoplanet atmospheres, an instrument designed for what he's going to be talking about tonight, which is the EXCITE experiment. He's been involved in researching neutral hydrogen intensity mapping, identifying low redshift galaxy clusters with the Arecibo telescope, and he's also been involved in physics education research. Tim is going to be talking about the EXCITE telescope, which is a near-infrared spectrograph, which is designed to be flown at stratospheric altitudes on a long-duration balloon platform from McMurdo Station in Antarctica. And it's the first dedicated instrument for observing exoplanet atmospheres. Sounds pretty exciting, and hopefully Tim will get a chance to go to the McMurdo Station and talk to us again about some of the results in the future. That's all I want to go into. I'd like to really looking forward to hearing Tim talk to us tonight. So Tim, if you're ready, if you could unmute yourself and begin, that would be wonderful.
Thank you for the introduction. Thank you everyone for having me here. It's a pleasure. Unfortunate circumstances that we do have to meet on Zoom, but nonetheless, we persevere. So let me share my screen. Let me just get the presentation ready. And
oh, and one quick thing, we will have some time for questions at the end of the talk, if that's okay with you, Tim.
That's totally fine.
Okay, thank you.
All right. So I am sharing my screen, and I am playing from the start. So, hi everyone. So I'll be talking about observing exoplanet atmospheres with the Exoplanet Climate Infrared Telescope. That's what EXCITE stands for. I know hopefully some people have, I'm not sure if people have seen some of this stuff before, if people haven't seen this stuff before. Regardless, I'm going to kind of walk through the science motivation behind it, and we're going to get into the experiment itself. So let's begin. So the outline of tonight's talk, we're going to talk about exoplanet detection, the status of where we are with how many exoplanets have been detected and how. We're going to introduce a kind of exoplanet called hot Jupiters, and we're going to talk about their atmosphere. And then we're going to answer the question, how do you observe an exoplanet atmosphere? So we have atmospheres on Earth and on all the planets that are in our solar system, except for the rocky ones close to us. But we're going to talk about how we're going to be able to observe one. We're going to talk about the EXCITE experiment. We're going to talk about its goals and overview, long duration balloon flights in Antarctica, why we're going to put this telescope on a balloon, what are some of the benefits and advantages to doing that. And then we're going to look at a few candidate targets that we're going to try and observe. So currently the state of exoplanet detection is pretty good. We have a lot of fancy space telescopes that are either in the work or that have been launched in the sky. Kepler, the now retired Kepler, had done a very good job at detecting a lot of exoplanets. TESS, the Transiting Exoplanet Survey satellite, has just been launched a few years ago and is currently detecting a lot of exoplanets. CHOPS, characterize, I believe this stands for Characterizing Exoplanets satellite, was recently launched. And then Plato, which is the Planetary Oscillations and Transits Observers, and that's going to be set to launch in 2026. And these instruments are dedicated to detecting exoplanets, not necessarily for doing atmospheric studies. So we look at the current numbers of exoplanets that we've, and then just to be clear to everyone, an exoplanet is a planet that orbits a star that isn't our sun. So a planet that's in a solar system, or that's in a solar system that isn't our own. And that's just what we call as an exoplanet. And so at this point, we've nearly detected 5,000 exoplanets, or have confirmed 5,000 confirmations. And you can see that that's rapidly increased in the past few years. From 2015 onwards, you can see that the number of exoplanets that have been detected has recently increased. And this green bar indicates that a lot of exoplanets have been detected using the transit method, which implies that the planet moves in front of the star from the point of view of us and therefore blocks the light. And we're going to talk about transiting exoplanets a lot in this talk because they're very important for atmospheric studies. But despite having 5,000 confirmed detections, we don't really know anything about their atmospheres. We really only know that exoplanets exist in bulk. And some of the things we'd like to know about their atmospheres are their chemical compositions, their temperature distributions, their dynamics such as wind speed, how fast are the winds moving on these planets? Are they hot on one side, cold on the other? Are they able to transport their heat very well? Do they have similar chemical compositions to the planets that we see in our solar system? It's to be determined. So I start with this plot here. And essentially we have the orbital period, or an exoplanet's year, on the x-axis, and then its mass and Jupiter masses on the y-axis. And these dotted lines tell you the mass of Jupiter, Neptune, and Earth. And the first thing to look at with this graph is that it's kind of spread out all over the place. You have planets that have been detected that have relatively long years and relatively short years, and then we have planets that are quite massive, above the mass of Jupiter, and almost to 100 Jupiter masses, whereas we have small planets that are smaller than Earth and almost Earth-like. And the thing that's most interesting, though, is that despite having this large kind of spread of different exoplanets, they're very different than the ones we see in our solar system, right? If this is the year on the x-axis, Earth would be about here, Neptune would be off the graph, and so would Jupiter. So these are planets, these exoplanets that we've detected are inherently different than the ones that we're going to expect based on what we know about our solar system. And you can see that there's two real groups of exoplanets, or two main groups that you can lump these into, and that's what we call the hot Jupiters, and then we're going to call these the mini Neptunes and super Earths. Now these are just categorical names when we divide. These are just names that we give to planets. There's no real boundaries as to what makes a mini Neptune or a super Earth. Plus you have all these planets in the middle here, which are often called hot Neptunes, in the mass range between Neptune to Jupiter. But the important planets to note are the hot Jupiters here. These are the planets that we're going to talk about a lot. They have the most interesting characteristics for atmosphere studies, and that's because they're bright. They're very bright objects. They're very large, and they have very short periods around their host stars. And because of that, that makes them great targets for atmospheric studies. If you think of a hot Jupiter as a gas giant similar to Jupiter, it's going to have a large atmosphere. And because it's close to its star, if it transits in front of it, then the star will be a good light source to send light through the atmosphere. So these planets make very good atmospheric study candidates for atmospheric studies. So let's talk about hot Jupiters. As I said, they're gas giants, and they're going to be composed primarily of hydrogen, helium, but and because they're very close to their host star, they're irradiated to very hot temperatures. So 1 to 3,000 Kelvin is the typical temperature range for these type of planets, and then Earth is only is less than 300 Kelvin in terms of its surface temperature. So these are very hot, very large planets, and you can see that they could have an abundance of different sort of metals, silicates, carbon monoxide gas. What's very interesting that a lot of people like about hot Jupiters is that the pressure is so hot, can be so high in the inner kind of down towards the core of the planet, that iron metal liquid is theorized to form. And so sometimes you'll read about planets, or you'll read about hot Jupiters that rain iron, and they rain liquid iron. And it's possible because you have these pressures that allow larger metals to form within the atmosphere, and so on. And you can have a bunch of different complex molecules such as methane, you have water, you have a bunch of silicates, and then sodium, lithium fluoride. These are all just a bunch of different chemicals that we know, or molecules that we know could exist in these atmospheres, that could reflect light, absorb light, emit light when it's irradiated by its star. And another interesting thing about hot Jupiters is that they're often tidally locked. So similar to the moon, around the Earth and is similar to Mercury around the sun, is only one side of the star or only one side of the planet ever faces the star. So, and that happens due to physics of tidal forces and friction on the surface ends up that these large planets become tidally locked. And because of that, there's a lot of things we can infer. If only one side faces the star, then you're gonna have one really hot side, and then you're gonna have one relatively cold side. And so that asks us, how well does heat flow from the day side to the night side? Is there and I write signs of habitability with a question mark here, because can a planet distribute heat in such a way where there exists temperature that could host signs of life, or could give candidates to potentially being habitable, right? It could be scorching hot planet, it could be scorching hot on the day side, but on the night side, it could be frigid cold, it could be freezing. And is there an in-between point where the temperature is actually kind of modest? And what's also good about tidally locked systems is that from the perspective on Earth, if they transit the star, which means they pass in front of it, they reveal phases. So just like the moon, you'll see a crescent, you'll see a gibbous, you'll see a half planet, you'll see a full planet. As it orbits around its star, it gets illuminated more and less depending on where it is in its orbit. So it's very important that hot Jupiters are tidally locked. So now we ask the question, how do we observe an exoplanet atmosphere? Well, the first requirement is we want the exoplanet to transit the host star. So here's the exoplanet, here's our star, that's when it moves in front of it. And so the star acts as a light source, right, from the perspective of Earth. And so any light that gets shown through this exoplanet's atmosphere could have some sort of absorption spectra, and we call those transmission spectra. And then conversely, on the other side, when the planet starts to go behind the star, we call that the secondary eclipse. And so in the first case, when the planet transits in front, you have the light passing through the atmosphere. In this case, you actually have the starlight would bounce off the planet and then reflect back towards Earth. And that's what we call emission spectra during secondary eclipse. And so we want to observe, so all these points are different observations we want to make while staring at a star-planet system. And then the fourth point I have here is to obtain a phase curve in optical and near-infrared wavelengths, because those are the wavelengths that we're interested in, because that's these planets being at 1,000 to 3,000 degrees Kelvin, they emit thermal radiation in the near-infrared. So they're the brightest in this wavelength band here to about 1 to 5 microns, or I put half a micron there. A phase curve is just observing a phase curve or obtaining a phase curve, we'll talk about all these points later, is looking at the change in brightness as a function of phase angle. So you look at the brightness when it's only a crescent versus when it's kind of almost fully behind. So when the planet's a crescent, it's going to be, the brightness will be a lot less than right before it sneaks behind the planet, because essentially its whole day side is facing us from our point of view. So let's talk about each one of those points a little bit more. So transmission spectra, right? So as the planet goes in front of the host star, this is here us on Earth, here's the star that we're curious about. This hot Jupiter moves in front of the star, and then you see the light. I've segmented the light in terms of different colors, even though from the star it's all white light. But as the different colors pass through the atmosphere, some get scattered and end up passing through, and some just scatter and get absorbed, while other colors will just pass through the atmosphere unimpeded. And then the resulting absorption spectra looks something like this here. And that can tell us, the abundance of molecules and atoms that are inside that are in the atmosphere. To first order, we can get a good atmospheric characteristic. And this plot down here on the right is a first look at one of those absorption spectras for a hot Jupiter. I believe the red curve is for a hot Jupiter. This is for a mini Neptune, and then this green curve would be for a super Earth. So I note here that some of the important molecular features that we would aim to resolve are water, carbon monoxide, and carbon dioxide. So this is called a transmission spectra. It's getting an absorption spectra during transit as the hot Jupiter passes in front of the host star from our point of view. And so then it travels along its orbit, and then it starts to go behind the host star. And then you get a combination of, and then the brightness that we observe is a combination of a bunch of things. It's the actual starlight from the host star that's not even touching, that doesn't even go through the atmosphere of the hot Jupiter. You have reflected starlight, you have starlight that's been reflected off of clouds, but then you also have thermal emission, and you have molecular features that get stimulated in the atmosphere due to the intense radiation of the host star. And so you can get an abundance of information about the temperature distribution and the molecular composition of a lot of the hot Jupiter's atmosphere. And what's also important is during secondary eclipse, when the planet is completely covered by the star from our point of view, so we don't see any star, at that point we're able to just get the flux or the emission spectra of the star, such that we can subtract it later on. It's kind of like our calibration for our baseline, and knowing our star is during secondary eclipse. So that's also very helpful. And I've written here that the thermal emission that we'd see is in the infrared, and a lot of the reflected starlight that would get reflected off the upper parts of the atmosphere, off of clouds, that's typically in optical wavelengths. So this, and now if you observe through transit all the way through secondary eclipse, the brightness profile that you'd get for a single wavelength is called a phase curve. And this is the phase curve that we see. We see this large dip here in brightness. Relative flux is on the left, and your orbital phase is on the x-axis here. You get the large dip in brightness is due to that transit. So the planet is obstructing the light from the star, but then we also get these two secondary dips as the planet goes behind the star, because the planet was emitting thermal radiation itself, because it's hot, because it has an atmosphere, and because it's generating thermal emission. You also get a dip there. And this is a closer view of these two secondary eclipse peaks here. And what we want to do is be able to generate spectra. If we can take the spectra of the light at this phase here, and this phase here, and this phase here right before transit, or this phase here right before it goes behind the star, then we'll be able to really extract and separate the molecular contributions to the thermal contributions, because you see a different part of the planet at different, you see more of the planet at different phases, whereas other phases you see less of the day side. And so what I've said here is, so we want to generate spectra at each phase for a range of wavelengths, and that's called phase resolved spectroscopy. And that's kind of the key term for this experiment here, is what we want to be able to perform phase resolved spectroscopy, is we want to take phase curves, we want to make these observations of hot Jupiters, but while we're doing it, we want to take the spectra of light at each phase, because remember, they're tidally locked. So at different phases, you're going to see more of just the day side of the planet. So you'll be able to see more flux or less flux just from the day side, which allows us to separate molecular components from thermal components. And then I've made this interesting little, or this map here is something that we can determine from a phase curve, is its offset and whether or not there's a shift in the substellar point. So you'd imagine that a planet that's being irradiated by temperature, the hottest point will be the point directly closest to the planet. One would expect that, because that's just the closest distance to the closest position of the planet to the star is the one right below it. But in this case, you see for some planets, that point is shifted a little bit to the east. And this is, so the maximum value of the phase curve of the relative flux actually happens just before the planet goes behind the star, which tells us something about the wind. It tells us that there's heat being moved to the eastward side of the planet, such that there's a shift in the substellar point, or the hottest point of the star. And that can tell us a lot about the heat transport of these planets, right? If this substellar point was way east, you know that winds probably are very high, and that heat is really being shifted from the day side to the night side. Whereas if you find that the maximum value is kind of smack in the middle, and that the maximum value peaks just before the planet goes behind the star, you know that the wind isn't very strong, and that the planet is not good at transporting heat. So these are kind of the techniques to observe an exoplanet's atmosphere through transmission spectra, through emission spectra during secondary eclipse, and then by taking phase curves. If we can do this all while obtaining spectra during each phase and performing phase resolved spectroscopy, we can do a real good job of characterizing the exoplanet's atmosphere. So as I said before, phase resolved spectroscopy is very important to exoatmospheric studies. And right here, this plot right here is one of those phase curves. This is a phase curve here. So each one of these lines is the spectra for a different phase. So this green curve is orbital phase of 0.5 here, then you have 0.62, 0.75, and then these are the different phases that relate to each one of these different curves. And now there's nothing really super illuminating just by looking at these curves. You can see that the absorption due to water is pretty broad. It covers a large range of wavelengths, but then again, this plot only goes from 1.1 to 1.7 micron because it was taken with the Hubble Space Telescope, which in reality isn't that large of a wavelength range to get good molecular features, or at least to discern multiple molecular features. You need to sample a large wavelength range. And then this is kind of an artist's depiction of what we're looking at when we look at an exoplanet's atmosphere. We're looking at this would be a similar phase to about right here, and this would be and then we would be able to determine whether or not there are certain amount of clouds on it, the cloud contribution, and whether or not there's a lot of water. So regardless, my point here is that phase curve analysis, getting those phase curves, is very common for detecting transiting exoplanets. I mentioned that at the beginning, is that exoplanet detections rely a lot on this phase curve analysis because you can see the dips and therefore know there is a exoplanet. But taking these spectroscopic phase curves, not many of them exist. So this is only one of 3 spectroscopic phase curves that I've been able to find, and very few of them exist. So why is that the case? It's because these are very resource-intensive observations. If you want to observe the entire orbit of one of these hot Jupiters, you're going to be spending, I say, 3 to 5 days per target, just because the orbital period could be 3, 4, 5 days. Some of them are actually shorter, could be 1, 2 days. But the idea is that you're going to have to stare continuously at a star-planet system for days at a time. You also want to get high altitude observations in order to avoid atmospheric distortion. Radiance from the sun and transmission issues really come up when you're on ground-based platforms, because we're trying to look in the near infrared. And you want a large wavelength range. As I said before, you want to resolve molecular features. And I said we want high altitude observing, so space-based is great, but allocating time on a shared observatory is tough and not always guaranteed. I can't always guarantee, now with James Webb Space Telescope up there, it's very unlikely that I could send in a proposal to stare at a target for 3 straight days for one phase curve or one spectroscopic phase curve. It's a little bit difficult. So getting time on these on large telescopes is something that's quite challenging, and that's why these are all difficult observations to make, and that's why so few of them exist. This one right here came from Hubble, and I believe different segmented observations, whereas the goal would be to do this continuously such that we can get the phase resolved spectroscopy that we want. So here's a picture of HD 1897 33b. I kind of do that to take a breather. It is known as it's a hot Jupiter that is primarily blue because of its reflection of magnesium silicates in its atmosphere. So I usually just stop here. I haven't brought up if there's any questions about hot Jupiters and kind of that overview. I don't know if I went through it quickly or not, but if there are any questions for that, I can pause now. Otherwise, I can just keep going on into the talk. All right.
I have a question. So what happens to water? I mean, water can vaporize and then is it not lost? Does
So
it become
water
part of the
will,
atmosphere?
yeah, so water will be lost. Here, let me go back a few slides. Water will be lost right around at these points here, kind of close to the substellar point. But because a planet is tidally locked, you have a very hot day side, but you also have a cold night side. So there could be a temperature around towards the night side or towards the terminator that could host water because it's less hot, if that makes sense. So water will get vaporized right when where the star hits the sun at the most intense, but water could also exist in other places in these planets because the heat transport could be poor or the night side could be very cold. It's actually possible that some of these hot Jupiters or some of these tidally locked planets show really hot day sides, but also could have potentially frozen ice on its night side.
And what about the other gases that, again, they can't, they're apparently not lost? Like carbon dioxide and carbon monoxide and methane.
Same sort of deal. Towards right on where the planet is being irradiated the highest, you're going to have mostly just hydrogen and helium because that's the only thing that isn't going to get blown away at that point. But larger molecular gases, they either are going to be deeper in the atmosphere, covered by clouds and other atmospheric layers, or they're going to be pushed towards the backside of the planet, towards the night side of the planet.
Thank you.
Yeah, of course. All right, so I'll continue on. I'll keep going. So let's talk. So I started the talk by talking about the state of the art for exoplanet detections. So now let's talk about the state of the art for exoplanet atmospheres. We have a lot of complex and cool space telescopes that are in the sky right now. One of which just launched, if you haven't known. James JWST is planning on can do these observations with its near infrared spectrometer on board. You also have the Hubble telescope, which is still alive, and it's still able to do these, but because it's in a low Earth orbit, it'd be very difficult, and you can't do it continuously. If you want to stare at a target for 1 to 2 to 3 full days, you won't be able to do that because Hubble is going to be on the opposite side of the Earth in 12 hours. So you need to segment your observations. Spitzer was a photometric infrared camera, and that recently retired. And then Ariel is the atmospheric remote imaging extra large survey, and that will be characterizing exoplanet atmospheres. But you can see that its launch is in 2028. So at the moment, and then of course we have JWST, which is on its way to the L2 point, the second Lagrange point, and that will be able to have similar capabilities to doing exoplanet atmospheres. But as it stands, there currently is no instrument dedicated to studying exoplanet atmospheres. All of these telescopes are shared observatories. You'd need to get time granted on them in order to perform these spectroscopic observations that take multiple days. So there's no instrument that's dedicated to doing this, and therefore not many spectroscopic phase curves exist, and we still don't know much about exoplanet atmospheres. And that's what brings me into that's kind of the lead into the Exoplanet Climate Infrared Telescope, which is Excite. So it makes a lot of puns, and we have a lot of puns in our group meeting for Excite. No one can say the word exciting without seeing a bunch of sneers and giggles. But regardless, it's going to be a balloon-borne telescope carrying a near-infrared spectrograph. It's going to have moderate resolution. Its Rayleigh criterion is around 50. Its passband, it's going to look from 0.6 to 4 microns. So it's going to look in the optical and the infrared and the near infrared. And what we're doing is this telescope is aimed to continuously observe hot Jupiters from McMurdo Station in Antarctica. We're going to talk about flying long duration balloon flights and why that could be beneficial for the type of observations we're making. So this is kind of the CAD model of the telescope inside the gondola right now. Unfortunately, we've just left the design phase of the telescope, but we don't have anything physical yet. The the items are on their way. They've been ordered and everything's been manufactured. And so hopefully within this year, we're going to actually be able to start putting it together and get some pictures. But for now, we have to rely on the CAD model. So we're going to go over, so I'm going to go over kind of the technical aspect of the telescope really quickly. This is a semi-custom Ritchie-Crichton telescope. The idea is to have a hyperbolic primary mirror. It's going to be about a half meter, 500 millimeter primary mirror, and then it has a 128 millimeter secondary mirror located here. And then it has these 4 in-bar spider mounts, which support the M2. This whole baffle length is about 1,000 meters long. So it's about 1,000 millimeters long. So it's about a meter. It's about a meter in length. And then there's 3 pistons and a motor that control the tip tilt stage of the secondary mirror, whereas there's 3 large collimation screws here, which allow us to finely adjust the primary mirror to sub-arc minute precision at this point. The actual assembly of the telescope, so this is the telescope is inside the gondola here. On the back side of it, you have the cryostat. This is the cryogenic component of the telescope. This is what's going to house the detector and the optics. The actual spectrometer is located in here. We're using pulse tube cryocoolers to keep everything cold. Normally in a lot of balloon flights, you'll opt for something like liquid nitrogen or liquid helium, depending on the temperatures, depending on the cryogenic temperatures you need. But that adds a lot of complexity, it adds a lot of mass, and it adds a lot of cost to your telescope to have to worry about a liquid solution. So we're trying to use these kind of commercial pulse tube cryocoolers to see if they'll effectively get the temperatures that we want. And then they themselves generate heat. And so we're going to have to dump that heat using copper methanol thermosiphons and attached to aluminum radiator panels, which, as you can see, stick out and they face space, or they're going to face away space, and we'll be able to radiate heat away. That's parasitic heat that's generated by these cryocoolers. They get transported to these plates, which ends up getting radiated away to space. This whole thing is about 65 inches long. This telescope, this is the telescope assembly. And then these 2 are dovetail plates, and that mounts this whole assembly inside the gondola, inside the telescope gondola. And here's a good cross-section of what it all looks like when it's inside the gondola. So we have nearly 3 orthogonal axes that will be able to rotate the telescope such that we can have control: the yaw, the roll, and the pitch. The yaw is pretty much your azimuth, and that's controlled by a flywheel and a pivot. And then you have down here a reactor wheel, which is used for momentum dumping, such that any rapid changes in movement from the balloon don't affect the payload and don't affect the gondola as much that we'd like it. And then you have the control computers are located above here in the inner frame. This is the cryostat, the inside here, and we have a piezo actuated tip tilt mirror, which can give us less than 0.05 arc seconds line of sight stability, which is very good pointing. So the gondola is pretty large. This stands at about 9.5, I believe it's 9.5 feet total together. The one thing that's not on here is the sun shields, but I think in the next slide you'll be able to see them. So, right, so we're going to be able to change. So the different axes here, you have the yaw, which will be able to move the azimuth. The roll rotates the actual telescope portion, and the pitch will determine the actual elevation angle there. So here's a picture of the gondola that we'll be using. So Excite will fly on the same gondola as the SuperBit experiment, which stands for the Super Pressure Balloon-borne Imaging Testbed. So SuperBit was one of kind of the pioneers of balloon imaging, of like high precise or very, very sub-arc second pointing astronomical imaging from a balloon platform. And this is one of, and so SuperBit was able to do that well. Its gondola is, and so we're using this pretty much the exact same gondola. Here you can see the sun shield panels are attached here. This is similar to the photos that we saw before. And then the sun shields also act as a power source for Excite. And so, as I've noted here, this has successfully achieved sub-arc second pointing stability. And you can see the gondola attached to the balloon here. This is Superbit in 2019. This was Superbit in 2017. So our telescope is going to look essentially, from the outside, it's going to look like this. The shiny multi-layer insulation there is to make sure that any radiant heat or radiant light coming from the sky or coming from the ground just gets reflected away. And so this is what the gondola looks like. The actual cryostat. So before, this is at the end of the telescope. This is the bore, the end of the bore site here. This is where the light comes in. And so the cryostat here, essentially we have two thermal goals. We want to maintain the spectrometer, which is the optics portion, which is where the light is going to bounce through mirrors and dichroics, and the readout electronics. We want to maintain those temperatures at 100 Kelvin. And then we want to keep the actual focal plane array, the detector, we want to keep that at 50 Kelvin. And to the right here, this is kind of an exploded view of what the cryostat looks like. It's just a real fancy thermos that keeps the readout electronic controller here. That keeps it at 100 Kelvin. You have one cryocooler is going to be used for each different temperature, one for 100 Kelvin, one for 50 Kelvin. And then you have different stages here. So this portion right here, you can see this is the input field stop. That's where the light enters the cryostat. And then this is the spectrometer. This is the 100 Kelvin shell, which is going to cover and keep closed the spectrometer. And then we have the 300 Kelvin shell, which goes on the outside. We call it the 300 Kelvin shell because when it's going to be in the stratosphere, when it's going to be miles from the surface, it's very cold and the ambient temperature is about 300 Kelvin. So it's very cold regardless, but we need to get colder. And that's why we have that outer shell. This is a top-down view of the cryostat. We can quickly look at the spectrometer here. So the spectrometer is the spectrometer essentially is going to split the light into two different components before it enters the cryostat. So here's a ray diagram of what the light paths are going to look like. You have the incident light coming from the telescope, bounces off a mirror, and then it meets its first dichroic at D1. And then you have an optical component is sent to a fine guidance system. And then you have your near infrared component, which is sent into the cryostat. And that is what's going to that's what we're going to use to obtain and detect spectra for these different hot Jupiters. And so the optical component is going to get sent to a Finger Lakes instrumentation liquid-cooled camera. And so that'll be able to help the pointing system for the gondola and the star cameras stay aligned. So essentially we take a part of our beam and we use it just for the star cameras and just for positioning and making sure that we have the proper line of sight stability. And then the rest of the component, the near infrared component, is sent into the cryostat, and that's used to obtain the spectra. And this is kind of an in-depth look of, this is kind of an actual ray tracing diagram of this of the spectrometer. Light enters a slit here, and then it is bounced off multiple mirrors and then a collimating mirror before it reaches a prism right here. And then the prism here, that refracts the light. What the prism does is the prism spreads the light out into its wavelength components, and then again the beam is going to be split and it's hit into an Offner relay where it is read into the detector, which is this box right here. So that's the scheme that we're going with in order to detect to obtain these spectra. That's kind of the technical view of the telescope. So now let's talk about long duration balloon flights. So we're going to be in Antarctica. This is a picture of a balloon right here attached to some payload. And this is McMurdo. This is kind of just a wide field view of Antarctica. And we're going to be flying on a long duration balloon flight from McMurdo Station in Antarctica. An LDB flight is what they're usually called. You have long duration balloon flights are LDB, and then you have ULDB, which are ultra long duration balloon flights, which we aren't doing. But typically the flight lasts for 11 to 30 days, And then we're going to be sent into stratospheric altitudes, about 40 kilometers or about 25 miles above the Earth's atmosphere. And at this point, we're above pretty much 99% of the atmosphere. I think it's like 99.99% of Earth's atmosphere is what we're going to be looking through. So we really do check off the box of high-based observing, such that we can eliminate a lot of atmospheric distortion from our signals. And then this flight hopefully lasts upwards of a month. It's in the stratosphere, it'll be up there, so we can observe multiple targets. And what's crazy about this balloon is that when fully inflated, it's 40 million cubic feet, which is essentially the size of an entire football stadium. And it's made out of less than 1 mil thick polyethylene film. So imagine a balloon inflated to the size of a football stadium, yet it's pretty much not even as thin as a sandwich wrap that you would wrap your sandwich in. So it's kind of mind-boggling. And the way that the balloon is carefully engineered, it has strips in it, and it kind of has like peels, like you would peel a banana back. It has slits in it such that it's maximally stable while being so thin. So these balloons are quite a feat of engineering. And something that's also something that's very helpful about viewing in Antarctica or observing in Antarctica is the circumpolar vortex. So there are winds in Antarctica that move in a circle at all times, especially at stratospheric altitudes. You have the circumpolar vortex creates winds that are always moving in a circle. So what you're able to do is when you set the balloon up into the atmosphere, up into the stratosphere, it's just going to drift very slowly in a large circle, and it's going to kind of go around the entire continent. And that takes about 15 days to go all around. And depending on the success of the mission and whether or not the launch was fine and everything, all the mechanisms work as expected, it could take one trip around the continent and even more. So you pretty much send the balloon in the payload, you send the telescope up there, and you hope it stays in orbit around the continent for as long as possible. And you can get that for a long period of time because you have the wind is always moving in one large circle. And that's important because then we can easily predict, and then we have an easily predictable flight path. It's not like it's erratic where you put the telescope up at 40 kilometers and then all of a sudden you have erratic winds that you need to take advantage of. This is usually, for the most part, you have a circular orbit, and it's pretty easy to detrend from the data. So this is a previous flight path of the E and B experiment, which went to look at the cosmic microwave background, the polarization of the cosmic microwave background. It's a previous telescope designed by Brown, which is why I included these two photos, because it also flew in from McMurdo Station, obviously, and you can see the path that it took. I believe it was in orbit for about 15 days, and you can see it drifts. It has different variations to it, but overall it does one full orbit or one full rotation around the continent. And this is the EBEX telescope on the large payload support vehicle. So this is the vehicle hangs the payload from here right before launch. And this is probably out there minutes before it was launched into stratospheric orbit. And so what's also good about viewing from Antarctica is that the sun never sets during the austral summer. We're going to be launching the plan is to launch in December 2023. So December in Antarctica is its summer, so the sun is going to be out the entire time, which may sound bad because the sun is going to be in your signal at all times, but it's better than having the sun set and then come back and then set, because then you have variations. Then you're going to have thermal variations on your payload, and your detector is going to read that. Whereas if the sun never sets, you have thermal stability, and you can easily subtract the contributions from the sun. And that's why it's advantageous for full orbit observations. It's tough to do these spectroscopic phase curves from Hubble because Hubble orbits low to Earth. And therefore, it's not going to be facing the same area in 12 hours. It's going to be facing the other side of the sun. Whereas we can launch a balloon from Antarctica, in 30 days, we'll have the same sky. We'll be able to view the same sky. And so a 3 to 5 day observation on one planet star system is perfectly feasible, and it's possible. So these are the reasons why we choose to do this in Antarctica, is because you have this thermal stability, you have the sun's predictability, it never sets, and then you also have this predictable flight pattern that it just moves in a circle. So it makes things very easy to keep things in the stratosphere for long periods of time. And what's good then is when we get good, by getting good observations from a balloon platform like this, we can then have justification, or we can have science follow up and say, hey, we observed these planets and these stars from a balloon platform, and we got interesting results. Now we want to go to James Webb Space Telescope and do a follow-up observation, and we're more likely to get the time allocated to us. So this is kind of the plan that we use when we're going about thinking of how to do these observations and how to maximize the science return, figure out, what are these atmospheres, what are they mostly composed of, how hot are they, and so on. So this is the benefit of observing in McMurdo in Antarctica. And so hopefully I'll be able to go down. I believe that is the plan, is to send me down there and hopefully be able to see the thing launch and it come down as well. So let's talk about a few. So finally, one of the things I wanted to talk about were some of the potential targets we're going to look at. Just checking the time. So if we look at some of the targets, so WASP 121 is a F6 star. It's a bit bigger than the sun in terms of its mass and its radius. It has a V magnitude of 10.4. It's 850 light years away, located in the Puppis constellation, and that's the star. So WASP 121 is the star, and then WASP 121b is the exoplanet. And this is I chose these because they actually have very short orbital periods. And so this is a 1.3 day orbital period, and the exoplanet is a little bit larger than Jupiter, 1.2 times the mass there, and it's quite bigger. It's almost twice, has almost twice the radius of Jupiter, and here's the sun in Jupiter for scale. So this is one of the targets that we're going to be able to look at. And another one is going to be WASP 95. So you can see I tried to change the color and the size to give an idea as to what the different kind of targets that we're looking at. This is a G2 star, a little bit larger than the sun again, but essentially it's very similar. This is a sun-like star with a magnitude of 10.1, a little bit closer and located in the Grus constellation. WASP 95b, the exoplanet that accompanies WASP 95. Anytime you see a planet that has a B or a C, D, E, it's the exoplanet, whereas the actual star is just WASP 95, its name. So if you have a solar system like the TRAPPIST system that has, I believe, 7 different exoplanets, you would label them as TRAPPIST B, C, D, E, F, G, H, in order as distance to the star. So the farther away they are, the lower the alphabet would be the classifier. So this star has a 2.2 day orbital period, and it's about similar to the size of Jupiter, but still a little bit larger. And then finally, another possible candidate is WASP 23. And I included here because this is also located in the Puppis constellation. This is the WASP camera. WASP stands for the Wide Angle Survey of Planets. It's a survey that's been done in South Africa and I believe in Spain, and it's used to survey a lot of stars and planets, and it's been able to host, and the results of this have found some very good candidates for transiting exoplanets. And that's what's common about all 3 of these, is that they're exoplanets, they transit in front of the star, or else we wouldn't be looking at them. So what's interesting about WASP 23, and I include it, is that it's a K1 star. So it's a lot less, it's less than the mass of the sun, it's smaller than it, and it has a magnitude of 12.7, so it's very dim. 675 light years away, also located near the Puppis constellation. So we're looking in, obviously we're going to be looking in the southern hemisphere. We're pretty much limited to the southern hemisphere considering our location. And then our planet here has a 2.9 orbital period, and it's almost the same size as Jupiter, but it is considerably smaller. So a point that I wanted to make is that these planets, these star systems, they could look like the sun and Jupiter, whereas WASP 95 is very similar stellar classification, and the planet itself is very similar to the size of Jupiter, albeit that it's a lot closer. Imagine in our solar system, if Jupiter was less the distance than that Mercury is, it'd be a completely different environment. So it goes to show that these exoplanet or these solar systems that we're discovering are not like the ones that we would expect given our own solar system. So you have planets that are the size of Jupiter orbiting stars that are a lot smaller than the sun, like WASP 23 is a K1 star. And so that's what's of interest. That's what I find particularly interesting about studying these hot Jupiter environments, is that they could be very foreign to what we expect. It's not abundantly clear why very large planets could form very close to their host star, because we understand Jupiter to have migrated outwards during its formation as a planet, whereas these planets that we're observing tend to incite that they were pushed inwards and closer to their host star, which is why they're so close and have a 2.9 day orbital period. I mean, the year of Jupiter is almost 100 years. So it's very interesting, and these planets hopefully return good science results and have they're likely going to all be tidally locked, and so therefore they're going to have a very hot side, and they're going to have a very hot day side and a very cool night side. And so hopefully there's some interesting heat transport that's going on these planets. And this slide shows us that for this is an intended schedule that we could be able to look at for an 18-day long duration balloon flight. This is kind of what would look like on our actual detector. Is we'd start with WASP 121 and WASP 23. You can see WASP 95. Those are the 3 planets we just talked about. And so we're going to be able to observe multiple full period systems. We can observe multiple full periods for multiple systems. It looks like for WASP 19, WASP 18, WASP 05, we'll be able to get 2 transit depths. You can see that these are essentially the phase curves that we were talking about before, just layered and stacked one after another. And so that's all we're trying to do, is to get these phase curves for multiple systems at multiple wavelengths and to get spectra of them. And in all, this is a project summary. So despite many exoplanet detections, there's about 5,000, as I said in the beginning, little is known about their atmospheres. Very little is known about exoplanet atmospheres. We have the chemical understanding of what we should expect there to be in terms of mixing ratios and abundances. Like, we know the planets should have an abundance of hydrogen and helium, just because there's an abundance of hydrogen and helium in the universe and in these stellar systems. But little is known about kind of their atmospheric dynamics and what the more precise ratios for these molecular features are. We talked about hot Jupiters as bright, short period gas giants. I mentioned before, imagine Jupiter, the distance away from the sun that Mercury is, in closer. So these planets are great for atmospheric studies. They're large, they're puffy, they have thick atmospheres. And therefore, the light that shines on them, they generate spectra, and they generate absorption and emission of the molecular features that are inside them, which make them great for these exoatmospheric studies. We talked about the Exoplanet Climate Infrared Telescope. EXCITE is a balloon-borne experiment that will perform phase-resolved spectroscopy. So it'll perform spectroscopy at each phase of a transiting hot Jupiter as it orbits around its star. And because of that, we'll be able to see different portions of the day side at different times, and that'll allow us to separate thermal contributions from molecular contributions and whatnot. So those are the critical observations. So exoplanet atmospheres require phase-resolved spectroscopy to be done, and at the moment there really hasn't been much. There have been very little results done to perform phase-resolved spectroscopy, because they're very resource-intensive observations. They take a long time. You need to be at a high platform, a high altitude, in order to avoid the atmosphere. And they're difficult observations to make. So in all, right, so the telescope, we have an engineering flight. This will be a test flight. Make sure that it'll launch, it won't fall apart on launch. We have it in Fort Sumter, New Mexico. We'll send the telescope down there in about spring 2023, maybe winter 2022, depends on when we can assemble the telescope and do the proper pointing alignments. And then our science flight, the multi-day flight in Antarctica, is planned to be in winter 2023. So as I said before, hopefully I'll be able to go down and we'll be able to see this launch and come down and get the data and be able to make some spectra. And so our first results are, the plan is to be spring 2024. So that's the summary of our project. I thank you for listening. And if you have any questions, please ask.
Thank you, Tim. That was really good. Is there any chance that you could use somebody to carry your bags to Antarctica? I mean, I'd be glad for that.
Sure. I'm sure the more the merrier. I don't want it to be too lonely.
I have a question. Will you be able to fully recover the telescope from the balloon and reuse it?
That's a really good question. The answer is, I hope we can. There are instances where the parachute doesn't deploy correctly, or the mechanism that unhooks the balloon from the payload doesn't work, such that you do have a telescope that could be ruined upon impact. That if I go back to the EBEX telescope, this telescope, unfortunately, what happened when it landed, the mechanism that let the parachute, once it lands, the parachute stayed on the telescope and the wind dragged it for almost 100 miles, almost destroying most of it. And they needed to take a helicopter to be able to find it. So the idea is, so hopefully it lands. For the most times, yes, it lands, and we should be able to use it with nominal damage, maybe on the outer part of the gondola, but the actual science instrument encased in the cryostat should remain untouched. But in some case of a catastrophic failure of some mechanisms, it is possible that large portions of the telescope can get destroyed upon landing.
Tim, I have a question.
Communication with the telescope during the flight.
Say it again?
What do you use to stay in communication with the telescope during the flight?
So there are two, I believe there are two remote, there's two remote locations on one side of the continent and the other, and they have some time relay systems, so we'll be able to downlink data. I believe I think our integration times are an hour long, and so I think after each one of those, we have like a certain amount of minutes that we sent to downlink data to each one of like the remote point, to each control center, but we will have internet access on the telescope at all time.
Tim, you said you were talking about thermal stability as important, and therefore you want to use the austral summer. What if you tried doing this experiment in austral winter?
So that's a good question that I'm actually not so sure. I guess my point was the sun never setting. It's good for thermal stability because it's always, you either always have it there or always don't have it there. My only issue with it launching in the winter is you might not be able to get the certain targets that you want because you're going to be looking at a different sky. And we're really limited as to what targets will be best because you really need these hot Jupiters that transit the star, or else we don't have any real science return. So I think we're able to maximize our science return in our candidate target list by doing it in the austral summer rather than the winter. And then just living with the sun contribution, being able to subtract that out.
I have 3 questions. Is it okay if I ask?
Go ahead.
Are you assuming that the planets, the exoplanets that you have molten cores that have magnetic fields that keep the atmosphere on the planet?
To first order, yes. Yes, they should have. They should be large enough to have some sort of magnetic field that keeps them close. But the gravitational pull of the planet is the primary factor that keeps the atmosphere in close to the surface of the planet.
Right. The next question is, what's the price tag?
$15 million.
All right.
So this isn't your $10 billion James Webb launch. We're going to be able to do this for kind of a fraction of the cost when you look at it in that way.
Right. Can you see noble gases on any of these atmospheres?
It's a good question. I'm not 100% sure if they would be in abundance. I don't think for our experiment, we're not going to be able to resolve any noble gases. They usually are pretty inert, as in they don't really react with much of the intense radiation. And in the wavelengths that we're looking at, I don't think there are any noble gases.
No. And the last question, geez, I forgot it. Just give me a second. Oh yeah, have you ever seen an exoplanet disappear?
An exoplanet disappear?
Yeah, I mean, you know, you've been tracking and you know where it is, and then you go back there and it's not there.
I haven't had that experience yet. I'm sure. I mean, there are cases where exoplanet detections have been sure that like a transit has been occurring, and then it ends up not being an exoplanet or something like that. It ends up being a satellite that was in near Earth orbit that you thought was a planet that was just doing something rhythmically. But I'm not sure about a planet actually disappearing or leaving. That'd be interesting. I haven't seen one personally myself.
Okay, thank you.
No problem.
Got a question.
Go ahead, Bob.
About the sensitivity of your spectroscopic instruments. Are we talking about less than 10 millimagnitudes in the transit depth, and on the eclipse depth, how deep is that? In the order of a 1 or 2 millimagnitudes?
Yeah. So I don't know the conversion in magnitudes, what the actual brightness dip is, but in terms of the flux that we receive on the spectrometer, the transit depths are on the order of a few, like 10,000 parts per million. And then the eclipse depths are going to be something on the order of a few thousand parts per million. And so that's the kind of the relative size, and the dip in brightness is on a function of, if I go back to these phase curves here. So yeah, so the relative flux here. So this depth here is kind of on the order of 1,000 parts per million. And then this depth here would be anything like 10,000 to 20,000 parts per million.
Yeah, at those levels, millimagnitudes and flux are approximately equal.
Yeah.
I'm trying to detect the transits of like a 12th magnitude star at a relative flux of like 10 parts per million.
Mm-hmm.
Is that the same range that you're talking about here? Is that?
Yeah, essentially. Yeah, we're trying to get our precision. If we're able to model our data and detrend a lot of the correlated noise and model the uncorrelated noise, we're trying to get within 20 parts per million resolution.
At what magnitude is the star?
These range between 10 to 12. The brightest that we'll be able to see is like 9.5.
Okay, I'm trying to do the same thing in the optical photometry area.
Yeah. You should have success if you look at it a long period of time. The biggest thing, in my opinion, the biggest difficulty would just be removing. It would be the atmospheric distortion, but in the optical, it shouldn't be that bad, especially at night.
Yeah. Well, the problem I have is I don't have very many clear nights here lately. Really bad weather-wise.
Yeah, that's the best part about being in the stratosphere. No cloud is going to be above us.
Sounded like the cat had a question. Jim?
That wasn't mine.
Yeah.
If by chance the telescope kind of floats back down to the ground safely, will you be able to send it up again?
Yeah. So, the gondola right here, this gondola was used in 2017, and then it was also used in 2019. So with essentially, essentially it's got probably the same telescope and a lot of the same kind of panels that are on it, the same sun shields, I'd imagine, unless anything broke. But the plan would be to send it up, hopefully it comes back down safely, and then send up a next generation spectrograph, or try and improve our cooling techniques, or if there's any other science return that we can get, different things to look at. So that would be the goal, yeah.
Thank you.
I have another question. How long does it take to get a spectra? How many data points could you get with this telescope?
So if we look at if a planet, so we can get spectra at phase angle. So we do hour-long integrations, and then if we look, and if the planet has an orbital period of 2 days, then an hour there would give us about 48 data points, 48 spectra throughout the orbit, minus maybe a few for downlink and sending data back and then recalibrating and stuff like that. So per orbit, I'd say we could get about 40 spectra, 40 data points at least. And then per spectra, you have a wavelength range from 0.8 to 4 micron.
Okay, thank you.
Well, I guess
I have a question.
Mhm.
What is the detector's resolution per pixel?
The resolution per pixel?
Yeah. More or less.
I'm not 100% sure. What do you mean the resolution per pixel?
Well, okay, is this detector a CCD device or?
It is a CCD.
Yeah, okay, so so it has a pixel array of so many pixels by so many pixels, right?
Mm-hmm.
So on this scale, how many pixels would be like in 1/10 of a micron of wavelength?
Oh, so we're using a 2048 by 2048 CCD, and so 100 rows, I'd say maybe 100 rows of 2048. So 200,000 pixels, 20,000 pixels. Did I do that right? Would be the resolution per spectra.
Yeah. Okay. So divide that by 40. All right, thank you.
all right, it's getting to be like 8:20. So unless anybody has any other burning questions, I think it's probably about time to wrap up this meeting tonight. I enjoyed this very much. I think it's been a great talk, very informative. And, hopefully at some point you'll have some information about, with some results, and you can come back and talk to us and hopefully actually visit the observatory too.
Yeah.
Hey, call us from Antarctica.
I'll have to do, when it launches, I'll have a video of the launch and everything. I'll have to really document it.
Yes, that would be great.
Yeah, I'm excited to get into the actual instrumentation part of it this year. Get the actual telescope. It's a shame I didn't have any actual photos of it yet, because we kind of just leaving the design stage of it. But
actually, I do have one other quick question. Who is fabricating the telescope?
Officina Stellare. It's
oh, okay. Yeah, I've heard of them. Yeah.
Yep.
Okay, terrific. All right. Well, I appreciate it very much. Thank you for joining us, and thank you for bringing your groupies, family members. Great.
Excellent presentation.
It was good.
Thank you so much.
Yeah. Thank
Thank
you.
you, everyone. It was a pleasure.
And I hope to see
right.
most, if not all of you, back next month for our next talk with Jan. Thank you.